Good morning to all of you in the session of thermodynamics. I welcome you all to this session. Now first I will at the outset I will describe you what the subject thermodynamics is, what is its contents, which is very important to know before going to learn this subject. Now the word thermodynamics originates from the word therm, that is a Greek word. You can write this therm, T-H-E-R-M-E, therm is a Greek word which means heat, and dynamics which is force. This originates, the word thermodynamics originates from these two words. This is the classical history of thermodynamics. Little bit you should know this thing. In primitive days or primitive understanding of thermodynamics centered around the concept of getting power from hot bodies or getting power from heat, abilities of hot body to produce work, which you can tell, which is partly the scope of mechanical engineering thermodynamics today. But the scope of thermodynamics is much wider or much broader. So before going to define the subject thermodynamics in a formal way, I just tell you like this: thermodynamics is probably encountered in our daily life. How? In all corners of physics. Just to start this way, before going to give a formal description or definition of thermodynamics, there are several physical processes that occur in nature, you know. There are some spontaneous processes that occur in nature. There are certain processes which we cause to occur in nature for our own purpose. But you know, all these physical processes are not at random or occur in any arbitrary way. There is always a rhythm for all physical processes in nature to occur. Even if you see the random motions of molecules have got a typical correlation coefficients or correlations. Probably you have heard or you have learned these things at first year level, at school level, and statistical properties are defined. Similar is the case of turbulence in fluid flow. So this way all natural processes in nature have got a rhythm. They occur with certain directional constraints that I will discuss it in detail afterwards. For an example, I tell you, you know the spontaneous processes, that the water falls from a higher elevation to lower elevation. Heat flows from high temperature to low temperature, not the reverse way. But there are many processes which we cause to occur, they also do not occur in the reverse way. For example, you know the conversion of mechanical energy into heat or intermolecular energy is possible. For example, if you stop a moving body, the body becomes hot. That means mechanical energy is converted into intermolecular energy. Well, but the reverse doesn't happen. But at the other end, there are many processes which can be caused to occur in both the directions. For example, you can heat a body, you can cool a body. You can expand a gas, you can compress a gas. But in those cases also you will see that there is some change in the external surroundings when you cause the process to occur in both forward and reverse directions. That will come afterwards in detail when you will discuss the second law of thermodynamics. That means today at this moment we want to tell that all natural processes occur with certain rhythm. There are certain natural laws and natural constants imposed on these processes. Now if you consider the conversion of energy, which is very important in the context of thermodynamics, transformation of energy or transfer of energy from one system to other system, there are certain basic laws to be followed. For example, the law of conservation of energy, which we know since childhood. But at some point of time we have to know this law. That means energy can neither be created nor be destroyed if you keep aside the conversion of mass to energy. Otherwise the mass plus energy is conserved. But if we keep aside that particular physics where mass is being converted into energy, we can tell that total energy is conserved. So this is really the first law of thermodynamics. So at one point of time we have to know. Another thing is that when you convert energy, in this case, the conversion is not efficient in all directions. Just for an example I am telling you, these are all popular things, you know, I tell you. For example, if you want to convert mechanical energy into electrical energy or electrical energy to mechanical energy, generator, motor, principle, you know, you can conceive physically an ideal system where 100% conversion is possible without violating the conservation of energy principle. True. But if you want to convert heat energy into work continuously, then 100% conversion is not possible, even in an ideal case. That means physically also we cannot conceive this thing. So these are the constraints. But if you do the reverse, you convert mechanical energy into heat. Just I told you, a moving body may be stopped to generate internal energy or heat. If you make the system insulated, so that entire kinetic energy can be converted into heat energy or intermolecular energy more precisely, this does not violate the conservation of energy. You cannot get more, but you can get 1:1 correspondence if there is no loss. But it is not so when you convert heat into work. So these are the directional constraints on the processes where transformation or conversion of energy is associated with. That means we see that for all natural processes involving energy transfer, energy conversion, there are certain rhythm, there are certain constraints, directional constraints, quantitative constraints imposed on these processes. Who tells? Which subject guides these principles? That is thermodynamics. Moreover, the relationship between the properties, physical properties of these systems which are affected by these processes are also being established by the science of thermodynamics. Well, so with this knowledge we can define thermodynamics like that, which you can get in book. You don't have to write this thing, that thermodynamics is a fundamental subject that describes the basic laws governing the occurrence of physical processes associated with transfer of energy or transformation of energy. And also it establishes the relationship between different physical properties which are being affected by these processes. This is the domain of thermodynamics. Now the entire subject thermodynamics is based on laws of nature formed by our observation and common experience. That means if you consider the thermodynamics as a table, then the legs are nothing but the laws of nature, which are sometimes observed in nature by our experience, day-to-day experience. For example, we grow old, we don't grow young. The hair grow grey, not black. These are also part of thermodynamics. These are the directional laws, second law of thermodynamics. So these are led by the legs, that is the basic framework of thermodynamics, from the laws of nature by our observation or common experience, and at the same time by experimental observations in the laboratory, which frame the base work of thermodynamics. Well, now in thermodynamics there are two views. One is macroscopic views, another is microscopic or statistical views. It is not always true for thermodynamics. For all physics, probably at this stage you have come to know that there are two views. One is the macroscopic view, sometimes we tell is classical views, classical physics. For example, mechanics, classical mechanics, another is the quantum mechanics. One is the macroscopic views, another is the microscopic views. Macroscopic view is sometimes referred to as classical, the adjective classical comes, and microscopic view is the statistical. In case of thermodynamics, we call it a statistical view. These are all recapitulations of the basic things. Now, in macroscopic view, what we do? We fix our attention to certain quantity of matter or substance without going into the events occurring at the molecular level. All right, without going into the events occurring at the molecular level. And what we do? We specify the characteristic features of the system, which we will define afterwards as properties of the systems. Those are being affected by the processes or its interactions with the surroundings by some macroscopic quantities which can be directly sensed by human senses, can be directly measured. This is also not 100% true. Afterwards we will see in thermodynamics there are properties which cannot be sensed by human senses or even cannot be directly measured, but at least they can be related by some expressions with some primary characteristic features or properties which are directly sensed or measured. And those relationships are established either by theory or by experiments at a macroscopic level. So this is the domain of macroscopic thermodynamics or classical thermodynamics or the classical physics in general. Whereas in microscopic view, what we do? We try to analyze the behavior of a certain quantity of matter from its molecular actions. That means we go into detail into the molecular activities. So that is the microscopic or statistical view. So the relationship is very simple, that macroscopic behavior is always explained through the behavior of individual molecules. This is because any matter or substance is composed of number of molecules. Okay. So therefore one can relate that way, that any macroscopic behavior can be looked as an average over a long period of time of different or a large number of microscopic behaviors, okay, or microscopic characteristics. But here one very important thing is that microscopic behavior or any explanation or any theory in microscopic behavior may change, but this has to be calibrated against the macroscopic behavior. You understand? For example, just I give you an example that we know that pressure is a macroscopic property which we sense and which can be directly measured. But what is its microscopic explanation? The pressure is because of the change of momentum due to molecular collision. That means if you want to find out the pressure exerted by a fluid on a wall, you just explain from molecular point of view that it is the time average of the change of momentum due to molecular collisions. That means the average of the change of momentum due to molecular collision taken over a large time. Now, if this theory changes little bit in the molecular level, at the molecular level, but the pressure, its sense, its measure, its change with certain other pertinent parameters remain the same, because this is the truth. So, any molecular theory has to be calibrated against the macroscopic theory or macroscopic observations, and it must have the capability of describing the macroscopic behavior. So, therefore, what macroscopic science or classical science tells is the truth. You understand? So, that is the relationship between classical physics and the quantum physics, or the classical thermodynamics and the microscopic or statistical thermodynamics. This you should know at the beginning to appreciate the course. So, our course will focus only on classical thermodynamics. So, some basic part of the classical thermodynamics at your undergraduate core level course. Now, with this introduction, now I will tell you the course outline of this course package. This is the first session. So, now I will show you. You see, the first one is, you can read it, you can take it, but I will distribute the handouts, that the prints to you, so you may not have to write it. So, first is introduction, basic definitions of systems and surroundings, thermodynamic properties, temperature and zeroth law, thermodynamic state, thermodynamic equilibrium, thermodynamic concept of energy, modes of work and heat transfer. Actually, this part introduction forms the basic background of understanding the other things. That means this gives the basic concepts and introductions. Then after that, if you see the first law of thermodynamics, then we will go to the first law of thermodynamics, referred to cyclic and non-cyclic processes. This all I will describe. Concept of internal energy of a system, conservation of energy for simple compressible closed systems, definitions of enthalpy and specific heats, conservation of energy for an open system or control volume. Next, the second law, which is very, very important. Second law of thermodynamics is very important. Now, in this context, I will tell you something afterwards. The directional constants on natural processes, formal statements, concept of reversibility, Carnot's principle, absolute thermodynamic temperature scale, the Clausius inequality, entropy, entropy balance for closed and open systems, principle of increase in entropy, entropy flow and entropy generation. Next is the availability. So, this is another part of the second law, it is a corollary of the second law, availability referred to a cycle, definitions of availability function for closed and open system, availability balance for closed and open systems, availability and irreversibility, second law efficiency. This may not be known to you, all the terminologies. Thermodynamic property relations is very important. Just I told that thermodynamics is a subject which establishes the relationship between different properties when there is a change in the properties because of a process occurring due to the interactions between the system and the surrounding. So, Maxwell's equations, TdS equations, difference in heat capacities, ratio of heat capacities, Joule-Kelvin effect. Then properties of pure substances, a part of which already you have studied in your physics, phase equilibrium diagram, in different thermodynamic planes, PV, PT, these are basic properties of a system. Ts, S is the entropy, Hs, H is enthalpy, S is entropy, this will be taught afterwards in this course. Then dryness fraction, steam tables, Molière diagram, these are the things you will know afterwards. Clausius-Clapeyron equation, probably you have heard of it at your first year level or school level. The equation relating pressure and temperature during the change of phase of a system. Then properties of gases and gas mixtures. It is the equation of state, ideal gas, a part of which already you have studied at a school level. Avogadro's law, internal energy, that means this discusses the properties of gases, specific heats, entropy change of an ideal gas, virial expansion, law of corresponding states. These are the aspects of the gas laws, equation of state, properties of a mixture of ideal gases. Then thermodynamics of reactive system, which is also important when the reaction takes place, because chemical reactions are always there in many of the physical processes for our use. Engineers are much more interested of the reactive system, as because our basic interest centered around getting motive power from fossil fuel. So we have to go through chemical reactions, so it is very important. The first law analysis of reactive system, internal energy and enthalpy of reaction, enthalpy of formation, second law applied to a reactive system, condition for reaction equilibrium. Well, air standard cycles, Carnot, Stirling, Ericsson, Otto, Diesel, Duell and Breton cycles. These are the thermodynamic cycles, but I will tell you the implications of these cycles when I will teach it. Don't feel that this is something very boring, all these cycles, what is the meaning of it, that you will be knowing afterwards. So when I will, that I am now showing the course curriculum. There are implications of these thermodynamic cycles. There are air standard cycles, there are vapor cycles. Air standard cycles deal with air as the working system, vapor cycles deal with vapor, that means the system which changes from liquid to vapor phase as it goes around the cycle. So there are number of vapor cycles, Carnot cycles, simple Rankine cycle, reheat and regenerative cycles, vapor compression, refrigeration cycles. So now after that, this ends your course outline, text recommended, which is very important. Now in this context, I tell you the books which are shown here are all equally good and are all recommended in the same way, not that the way 1, 2, 3, 4 means the number 1 book is recommended as the best book. All the books are equal, but sometimes it has been found some chapters of some books are very good. Fundamentals of Thermodynamics by Sontag, Bronke and Van Wylen, this book will be available in our library. Then Engineering Thermodynamics by Nag, you know this is one of the best books in Indian market. Thermodynamics by Wark, Fundamentals of Engineering Thermodynamics by Moran and Shapiro, which is very good for these some aspects of second law, especially the availability principle, and Engineering Thermodynamics, Work and Heat Transfer by Rogers and Mahon. But I will not be following a particular book ditto for this course. My lecture will be a compilation of materials from all these books, even from books of by different authors. So you can consult any of these 5 books. You can purchase also Professor Nag's book if you feel so. You can get any of these books from the library. These are good books in the field, and you can consult any of these books as additional materials apart from my course. Now before I start the course, I like to tell you again one thing, that importance of thermodynamics can again be emphasized in 2 ways, just I tell you. One is the practical importance. What is the both are practical importance, but one is more emphatically, more emphasis can be given to the practical field, that today all of you know that we are very much aware of conservation of energy and its conservation. What does it mean? It means that nowadays we see that there is a threat of rapid depletion of fossil fuel. Our basic objective as engineers, here we are mechanical engineers and energy engineering students. So our basic objective to get mechanical power or electrical power from fossil fuel. But there is a rapid threat day by day, as you hear to TV news or you read, that there is a rapid depletion of the natural resources of fossil fuel. So therefore there is a concern for efficient utilization of this energy. At the same time, the access to the alternative energy resources, for example solar energy, wind energy, are limited because of certain inherent physical difficulties in the physical processes. So therefore we have to put more concentration, or we have to put more effort on efficient utilization of these energy resources. So to efficiently utilize the energy, we have to follow very strictly the rules and the principles which are being followed in converting energy from one form to other form. At the same time, we are concerned today about the environment. You know, we want a clean environment. That means whenever we transform energy to get power from its fossil fuel, in terms of chemical energy, geothermal energy, whatever you tell that energy in the fossil fuel, or energy stored in the earth in mechanical power, we will have to utilize it efficiently, and at the same time we will have to use it in a clean way so that the environmental pollution is less. So therefore, in doing so, all the processes which are necessary in doing so have to be known very clearly, and their basic principles are guided by thermodynamics. This is one way. Another way, you can ask me, sir, well, there are other subjects also, fluid mechanics, other branches of basic science and basic engineering and science subjects which guide also the principles of the physical processes. Yes, but thermodynamics is the primary one, which gives you the primary direction. Just for an example, whether a process is feasible or not, just I described little earlier, whether a particular process is feasible or not, and if it is feasible, to what extent it is feasible, whether it is feasible in all the directions or not. These are the things which will be told by thermodynamics. Another important aspect of thermodynamics, thermodynamics in this way tells us that there are certain things which you cannot do, which is very important to know, because in your life it is always much better to know which we cannot do rather than knowing everything which we can do. For example, if you miss some of the things which you can do in short lifetime, it does not matter, because there are number of things which we can do. We can miss some of it because we cannot cover all these things in our short lifetime. But it is very important to know which we cannot do. For example, if an engineer or scientist does not know that a heat engine with 100% efficiency can never be done, even in an ideal case, you understand? So he may put his entire lifetime effort to build a heat engine which will give almost 100% efficiency, but it will not be possible. Just like making the tail of a horse straight, it cannot be done, we know since our childhood. Okay, the tail of a horse cannot be made straight. So like this, there are many cases, you know that a reaction cannot be made to occur under these circumstances in a particular direction, but a chemist, if without knowing he always puts his effort to make so, he is a fool. So therefore, this negative statement, that means what we cannot do, is provided by thermodynamics, which is another aspect of thermodynamics of prime importance as compared to other physical sciences, that we can find out things which cannot be done, which comes from the law of nature. Okay. So with this now I will start your course, the subject. The very first I will recapitulate the definition of systems. Probably this has already been done in fluid mechanics course or in solid mechanics course. I don't know, not in solid mechanics course, I think in fluid mechanics course. It will be a recapitulation of that. Now you come, how do you define a system? Because in thermodynamics, whatever analysis will be done will be referred to a system. In all branches of physics, probably you have come across the definition of system, because the analysis or the law of conservation laws are all applied to a system. So therefore, we must learn carefully what is the definition of a system. This is a recapitulation. So now we will brush up your our earlier understanding. If there is any problem, you can ask me the question. So let me start like this. A system basically can be divided into two broad parts. One is the control mass system. Well, one is the control mass system. The control mass system. The word control mass is very, very important here. The two words control mass. Another is the control. Do you know what is another one? Very good. Control volume system. That's why I am telling you recapitulations. Okay. First one class will be recapitulation. Control volume system. Now you tell me what is the definition of control mass system. First of all, a system as a, in general, both the cases the system is common. So a system is always a certain quantity of matter on which the attention is paid, and this is always bounded by a boundary. So two requirements of system is that certain quantity of matter which is bounded by certain boundaries. Let this be the boundary. I hatch it like that. So a system has two characteristic features, certain quantity of matter and surrounded by the boundary. I cannot write everything this paper, so you can write it. Now this boundary may be a solid boundary or may not be a solid boundary. Sometimes this boundary may be imaginary type of boundary also. We can imagine certain boundary, but we have to track that boundary always to define the system, that means a particular quantity of matter as separate from the rest, that is the surroundings. Okay. Now, the two characteristic feature of the system is certain quantity of matter within a space which is defined by some boundary. This is known as boundary of the system. Boundary of the system. Now, this boundary separates the system from its surrounding. So, everything external to the system, that means on this side of the boundary is the surroundings. So, therefore, a system is characterized always by its surroundings, that means external to the system is surroundings. That means the boundary separates the system from the surrounding. Now, we come to these two things, what is control mass and what is control volume. So, control mass system is a system where the mass remains fixed by its quantity and also by its quantity, that is mass, and also by its identity. By its identity, not the volume. Volume may change, that is system boundary may expand, system boundary may collapse. It is the mass and identity of the system has to be same for control mass system. So, for a control mass system, mass plus identity fixed. So, mass plus identity fixed. So, when we define a control mass system by this thing, that mass plus identities are fixed, that means the mass is controlled, then automatically it takes care of the fact that there should not be any mass interaction. That means mass interaction M is 0. That means mass can neither go out of the system, mass can neither come into the system. That means the system boundary does not allow any mass interaction, because if the mass interaction takes place, you can make the mass of this system or the quantity of this quantity in the system same, because you can take some mass and you can add the equal amount of mass, but the identity will be changed. That means a closed system contains the same mass, that means there is no mass transfer across the system boundary. This is the basic definition of a control mass system, but there may be energy interactions. Energy, that means energy interactions may take place between the system and the surrounding in any of the ways. That means energy can come into the system, energy can go out of the system to the surrounding. That means a boundary of a closed system restricts the mass transfer, but does not provide any restrictions to the energy transfer. That means energy transfer is possible, but mass transfer is not possible. Whereas a control volume system, as the definition is control volume. So, what it should be? Which should be fixed? Only volume, correct? Volume fixed. But it is also not always true, there are deformable control volumes also. If you leave aside the deformable control volumes, under all usual conditions in a control volume, the volume is fixed. Usually you define control volume in that way, that it is a region in space which is bounded by certain boundary of control volume, which includes some quantity of matter within it, and this is known as control surface. These are the terminology. Control surface. That means the boundary of the control volume is known as control surface. Now, the identity may not be fixed, which means a control volume is a region in space bounded by a boundary known as control surface, which contains some matter, and the boundary may allow both mass transfer is not 0 and energy transfer. That means a control volume may, there is no restriction, that means may interact with its surroundings in terms of both energy and mass transfer. So, therefore, you see the total mass of the control volume may go on changing, but under certain conditions it may so happen the mass coming in and mass going out becomes equal to each other, so that the mass of the control volume remains same. In that case, in which way does it differ from the control mass system? Identity. Very good. So, therefore, this is known as the steady state control volume, when the mass coming in and mass going out remains the same, and energy coming in and energy going out remain the same, we will come across this thing afterwards. Then the properties of the control volume remains invariant with time. Mass being one of the properties become invariant with time. In that respect, it is almost similar to a control mass system, but difference is that the identity is changed. That means a control mass system allows the mass transfer to take place across this boundary. Well, now apart from these two main category of systems, classes of systems, another system is there which is isolated system. Isolated system. It can be better understood through a closed system. Isolated system, you can tell, is a closed system. Let us consider a closed system with no energy interaction, That means if you consider a closed system, its boundaries are such that there is neither mass interaction, there is no energy interaction. That means a closed system with no energy interaction. Closed system already has no mass interaction. So if you define with a control volume, you can do it, that control volume with no mass interaction, no energy interaction. That's why it is better to define from a closed system where already mass interaction is restricted, but along with that there is no energy interaction. In that case, the system is closed. That means there are only two ways by which a system can interact with the surroundings, in form of mass transfer, that mass can come out, can come in, energy can come in, can go out, so mass and energy interactions. So if both the interactions are zero, then a system is isolated. Then the properties of this system, whatever is there containing in the system, remains invariant in time. The system is not at all, is passive to the surrounding. So it has got no link with the surrounding. This system is known as closed system. Well, so now these are the definitions of these systems. Then I come to the definition of thermodynamic properties. Thermodynamic properties, which are very important. Thermodynamic properties. What do you mean by thermodynamic properties? Now, very basic definition of properties, you go back to our school level, because these are again recapitulation. How do you define properties? Very simple is that these are the characteristic features of a system, identifiable and observable characteristic features of a system by which it can be specified, by which a system can be specified. These are properties. For example, as you know, a system, if you specify, how do you specify? A system of certain mass, certain pressure, certain temperature, certain volume. These are the properties. That means any characteristic feature that specifies the system, that is the property. So there is nothing much to understand innate properties, but we have to know that how a system is specified. That leads to the definition of state of a system. That I will come afterwards. Before that, let me tell you that okay, there are some characteristic features by which a system is specified. Okay, this is the system of this mass, this pressure, this temperature, this volume, and there will be a number of such properties. Now next is that this property can be divided into two groups. One is extensive property, another is intensive property. So I write properties are defined, are distinguished in two groups. One is extensive property, another is intensive. Can you tell me the difference between extensive and intensive property? What is extensive property? Some properties are extensive properties. What are those? Depend on the mass. Very good. Extensive properties are properties which are directly related to mass, which depends on the extent of the system. That means which are directly related to mass. When mass is more, the extensive properties are more. If its mass is less, extensive property values are less. That means if the mass tends to 0, that means system collapses to a point. Then what is the value of these extensive properties? 0, because there is no mass of a particle. The examples of these extensive properties are mass, volume, internal energy. This we will see afterward. There is no internal energy at a point, enthalpy, entropy. And what are the intensive properties? Just the other way. Intrinsic properties are properties. No, this is second, that specific extensive properties are intensive properties that come afterwards. But what is the basic definitions of intensive property? The properties which do not depend upon the extent of the system or its mass. That means even if system collapses, it is not related to the mass. That means system, for example, internal energy of a system of certain mass of gas. If the system collapses to a point, internal energy goes on reducing to 0. But it is not so. That means it does not depend on the mass. On the other hand, when the system contracts to a point, the intensive property attains a finite value, just like your stress. How do you define stress in mechanics? That is force by area as area tends to 0, because stress is defined at a point. If a system has a stress, but the system contracts to a point, it is also having a stress. That means in a system, point to point, there are stresses. So similarly, here also, intensive properties are those properties, even when the system contracts to a point, it has a finite value, pressures and temperatures. We define pressure at a point. We define temperature at a point. So these are the intensive properties. Now next is that what you told earlier, correct, the specific values of the extensive properties. Now extensive properties are directly related to mass. This can be specified by their specific values, that means per unit mass. For example, internal energy per unit mass, enthalpy per unit mass. Well, then your enthalpy per unit mass, entropy per unit mass, this quantity is these quantities are intensive properties, because specific internal energy is defined at a point. You can look in this way, that internal energy per unit mass is the specific internal energy. Now when you tend the mass to be 0, you take a limiting value, then internal energy per unit mass reaches a finite value. That means both internal energy tends to 0 and mass tends to 0, and the quotient reaches a finite value. So that is the reason for which these specific extensive properties are the intensive properties. All right. So these are the two categories of properties. Now in this context, I will tell you, you will recognize it afterwards. Now initially we start with those things as properties which can be directly measured, which can be directly sensed. For example, pressure, temperature, volume. But you will see afterwards there are large number of thermodynamic properties. For example, enthalpy, for example, entropy, which cannot be sensed or directly measured. Sometimes it appears that it is abstract. It is not abstract, but these are being derived through certain postulates, certain equations, certain laws. So a broad definition of properties are these which specify the state of a system, that I will tell you afterwards, state of a system. So any parameter which is a point function or which defines the state of a system are the properties which may be or may not be directly measured or directly sensed. So this you keep in mind, so that we can identify many such properties of a system. Okay. So with this, now I tell you what is a thermodynamic state. Now when you define a system in thermodynamics, and immediately the question comes that okay, these are the properties or the characteristic features by which I specify the system. Okay, I tell that this is a system, it has got this pressure, this temperature, this internal energy, this enthalpy, and so on. Now question comes, if there is a distribution, how do you specify it? By which temperature? If I tell a system of temperature this, that means the system is having a uniform temperature. That means I quote only one unique value to specify the state of a system. So therefore the requirement is that there should be an uniform value of these properties throughout the system, even if the system is a finite one. So that requirement is very important. It may not be in practice, but to define the state of a system, it is a requirement. That means only and only when these properties are uniform throughout the system, we can specify this system by these properties. Otherwise there is no point of putting a single value. That means the first requirement to specify a property to fix its states is that all these property values should be uniform throughout the system. Well, and second is that this should not change continuously with time. That means this should be invariant with time, at least for a temporary period. Try to understand, I am not writing everything, at least for a temporary period. That means in practice what happens when a process takes place and a system changes from one state to other state, throughout the process the system always changes its state. That means at any instant of time the system is in a dynamic state. That means there is a continuous change of its property values. So we cannot define a state of a system that way, because how can you recognize the property? It is continuously changing. So it has to be fixed, it has to be invariant with time, at least for a moment it has to be invariant with time, so that for that moment I can specify the state of the system. This is a very important condition. So two conditions have to be satisfied. One is that the properties should be uniform throughout the system, there should not be any variation of the property. If temperature is a property, then temperature of the system has to be uniform, pressure has to be uniform, specific internal energy has to be uniform, this with respect to intensive properties, because extensive properties is the gross properties, total properties which are dependent on mass, but all the extensive properties should be uniform throughout the system and they should be invariant with time, at least temporarily for the moment when the state of the system is defined. Then only we can tell the system is at that state defined by these properties. Then otherwise it is meaningless. It will be meaningful when these properties are fixed, uniform throughout this system and invariant with time. So this is the definition, but this is the way how do you fix the state of a system. Clear? Now the next question comes, well, we know there are n number of properties, we can list on properties. You will see in thermodynamics we can go on entering properties in a list, and there is a big list of properties. If there is a point function, there is a property. Now you see that point function means why I am telling point function, because the state of a system is a point. That means state we can represent as a point in any thermodynamic coordinate diagram. So that's why sometimes the property values are told as, properties are told as state variables, or the point functions of the system, state variables. That means which define the state of a system. You understand it? Now question comes, there may be number of state variables or state point functions which describe the system, which are the characteristic feature of the system or the property of the system, like pressure, volume, temperature, internal energy, enthalpy, entropy, Gibbs function, Helmholtz function. You will learn all those things. Now the very pertinent question comes, to specify a system there must be some minimum number of independent properties, or there should be some independent properties to fix the state so that other becomes automatically dependent. That means out of n number of properties there should be some independent properties. You understand that independent parameters, like independent parameters, that means out of n properties there must be some m number of properties which are independent. That means if we specify the system by those m properties, other m minus n properties are automatically fixed by certain equations, the property relation. So we have to know what are the number of independent properties required to fix the state. Otherwise what happens? If I have to fix the state of a system, should I have to prescribe or quote all some 100 properties? That is system having temperature this, pressure this, volume this, internal energy this, enthalpy this, entropy this, Gibbs function this, Helmholtz function this. I cannot do like that, so on. So I have to know that what are the number of independent properties by which we can specify the state of a system. So this was given by Gibbs and is known as Gibbs phase rule, the derivation of which is out of scope of this class, but I tell you the formula that the number of independent intensive properties F is given by this formula, C minus phi plus 2. F is the number of independent intensive properties. What is C? C is the number of components, very good, number of components. Phi is what? Number of, very good, number of phases. This you have already learned at school level in physics. C minus phi plus 2. Now you consider a simple case where number of components C is 1 and number of phase 1. That means a gas, a single gas or a single liquid. That means component is 1 and it is in one phase, single phase. Then what is F? What is F? 2. Very good. That means only 2 independent intensive properties are required to fix the state of the system, which means that I can show in a 2-dimensional plane with x, y as the thermodynamic properties that this is a state of the system. Let this is 1. So a point, that means we can represent the state of the system for a single component single phase system as a point in a 2-dimensional property diagram, thermodynamic property diagram, where x and y represent any 2 such independent, any two of out of so many properties we can choose which are to be required to specify the state of the system. So if two properties are fixed, that means others are automatically fixed. Of course, this is for a single component and single phase, and we can relate from here other interesting things, that when C is equal to 1 but phi is equal to 2, what is the value of f? 1. What is this? This is a one component but two phase. That means if a component coexists in two phase, for example water and its vapor, steam, water and ice, solid liquid or liquid vapor, then only one independent parameter is enough. For example, if I tell water and air is in equilibrium, water and vapor, steam, that means the single component but two phase are in equilibrium at, there is a system which contains water and steam at 1 atmospheric pressure. What is the temperature? 100 degrees Celsius. That means temperature is also fixed, and when these two things are fixed, everything is fixed. That means only one parameter is sufficient to identify states. Another interesting result is that if C is equal to 1, and phi is equal to 3, what is f? 0. What is this? Triple point. Very good. That means the three phases can coexist in equilibrium and only at a unique state. That means there is no variation of state properties. That is only unique state, that is known as triple point. Okay. So the number of independent properties becomes 0 in that case. So we will be discussing mostly the cases with single component and single phase and single component in two phase in our course. Okay. Now this way we can represent the state points of a system. Now question comes that, sir, okay, we tell that a system state can be prescribed when this is invariant with time and this is uniform throughout the system. When we can get it? If the system continuously interacts with the surrounding, then properties go on changing, and there may be an internal process going on within the system. One part of the system, heat may be transferred to other part. So therefore the temperature, there may be a temperature gradient. For example, heat is being conducted through a rod, as you know. If you consider the rod as a system, there is a temperature gradient. That means from one part of the rod, heat is being transferred to other part. A heat transfer process is taking place, even if you take the rod as a system. Then in that case, this is not a system to be specified by a single temperature. So therefore, if we have to specify this system at a single with single fixed properties, requirements are like that. There should not be any process within the system, there should not be any process between the system and the surrounding. Alright, in this case we tell the system is in total thermodynamic equilibrium. That means it does not interact with the surrounding, and it is true that if a system is prevented from interacting with the surrounding, then automatically the system will come into an internal equilibrium also. That means the process within the system will cease after some time and the properties will be uniform. So the requirement for a system to be in equilibrium means that it will not interact with the surrounding, so that the properties will be invariant with time, and automatically any internal disbalance of the properties will die out, and ultimately it will give a uniform property by which we can specify the state of the system. Now question comes, sir, how can I make it? There are two ways of making. One is that you make the boundary such that in spite of a gradient, now when the process takes place, there may be certain imbalance of properties of surrounding and system, because system will interact with the surrounding. When there is an imbalance between the system and the surrounding, there is a affinity of a process to take place. So you can do it in two ways. You make the boundary such that no process will be allowed, just like an isolated system. For example, surrounding, there is a chaos in the surrounding, so your affinity is to immediately go out from this classroom, if you consider the classroom as the system, but I do not allow you to go out. That means the boundaries are such that it does not allow the system to interact with the surrounding by creating those boundaries. Another way, this is one way, even if there is an imbalance between the properties which can cause processes. Another way of doing this thing, that system properties are such that they are same with those of the surroundings. You understand? That means there is no difference or imbalance between the properties causing the processes between the system and the surrounding. And in those cases, systems are defined as dead system, or the state of this system is known as dead state, because a dead man cannot interact with the surrounding. So, dead state of the system. That means either the system has to be in dead state or the system is such that its boundary does not allow it to interact with the surrounding. That means it has to be isolated system. Then the next question comes from the student, said then you want to mean in practice if the systems are not dead, then only the isolated systems are systems where we can define the state of the system. It's the very interesting and very intelligent questions, and this is the question to understand the thermodynamic equilibrium. Yes, it is so. So what happens for all systems which interact with the surrounding, not isolated system, because interaction between the system and the surrounding is our goal. This process we want, from which we are benefited, we extract something. So system is never in equilibrium. So all the successive states are in non-equilibrium. But for our thermodynamic studies, we consider the system, the intermediate states, to be equilibrium in a limiting case. That in that case only we can specify the state points of this system. You understand? State points of this system, intermediate state points, that I will come afterwards when I will discuss the thermodynamic process. So therefore one should know only the state points 1, 2, 3 we can define when the system comprises of certain matter, are the properties are fixed, uniform, invariant with time and uniform, and we can define the state points of the system. Okay. Then next we come to the concept of equilibrium. Okay, today I think time is almost up, so I don't want to go with more materials. Well, you can ask any question. So far we have discussed, time is there, so I think it will be better if you interact. So far whatever I have told, if any questions are there you can ask. Yes, please.
So in case of control mass system,
Yes.
Like the identity has to be fixed.
Yes.
So suppose if a system has substance A, and the same substance, some part of it goes out in the substance, another substance, so the only A comes in. A.
No, A cannot come, because identity is fixed with one material only, one particle. There can each and every species having different identity. You have to conceive like that. You are only alone, you are unique in this universe. There cannot be any other person. Even with the twin brothers there are differences. So identity fixed means identity is fixed. One thing. Now here when we define the system and surrounding, good thing has come up, that the one system is interacting with another system, for example, then if you consider a system A interacting with system B, in that case system B is surrounding to system A and system A is surrounding to system B. That means interactive system, one is system, another is surrounding. Surrounding definition is very important. That means it is that part of the external things which interact with this system. For example, if two bodies are interacting with each other, with nothing on, with nothing other, then what happened? One is the system, another is the surrounding. A and B. A is the system, B is the surrounding. B is the system, A is surrounding to B. And these interacting systems together constitute an isolated system. That is very important. So what he is telling, that if system A interacts with system B, well, system B is surrounding to system A is surrounding system B. Whenever there is a mass transfer, neither of this system is a control mass system, because the identity is lost. Identity is unique. So therefore sometimes it is difficult to understand through identity. So better to understand it, there will be no mass transfer across the boundary of a closed system. All right. Any other question, please?
Sir, you just told that for the equilibrium condition to hold an ideal case, the system needs to be absolutely isolated.
No, that is the thing that you will be able to understand afterwards. To be in thermodynamic equilibrium, system ideally speaking has to be isolated, correct, or has to be dead state. This is true. Ideally 100% equilibrium means either system has to be dead, that means its property should be same as that of the surrounding, or it is to be isolated. But in normal cases, when a process takes place, there is an interaction between the system and surrounding, then it is never in equilibrium. But we conceive it in limiting equilibrium, that is known as quasi-equilibrium. That means we consider a process to take place for infinitely long time and system comes through several stages. That means there is a process with an infinite small gradient and it departs from initial state to a intermediate state and it stops there for some time. Again it's that. That means we divide the entire process to a large number of infinite small process. That I will explain in the next class, so that the idea will be much better and you have got a clear idea how we reach in practice, or how we can conceive in practice equilibrium states. But 100% equilibrium state means that either it is a dead state or it is isolated. That means by the boundary the interactions are being prevented. Okay. Any other question, please? Yes. Certain quantity of matter, yes. Whatever absolute vacuum, we don't define a system. Then absolute vacuum, the system is never defined. No system is defined in absolute vacuum. I tell you, in space technology, if you go, when a rocket goes to the space, no analysis is made with considering the surrounding as a system. You understand? Only the gas which is being ejected and the nozzle from which, the propelling nozzle from which it is being ejected. So if there is the absolute vacuum, the definition of system is not there. Consider the absolute vacuum never defines the system, and no physics deals with absolute vacuum as a system. Vacuum means what? There may be some material. Vacuum is a word which is used in defining the units of pressure. When the pressure is subatmospheric, we tell this is a vacuum condition. So gauge pressure is negative. That means some material will be there. That is a system. But absolute void, there is no absolute pressure is zero, absolute vacuum is not a system. Okay. Well, any other question? So I think this is all right for today, and I'll be happy that if you read before coming to this class and you interact this way. So that's why I am telling next class we will be describing that, as I have already shown, that thermodynamic processes. What is meant by thermodynamic process? The thermodynamic equilibrium in general. It consists of thermal equilibrium, mechanical equilibrium, chemical equilibrium, then concept of temperature, and the concept of energy transfer by thermodynamics. Okay? Thank you.